for the introduction, I'll leave the video open and then turn it off as the presentation starts. So hi, I'm the founder and CEO of Open Refactory. We are basically, our mantra is we fix code automatically. We are bringing in a solution to automatically fix security, reliability, and compliance problems in software. So right now we have solutions available for Java developers and C developers. So the specific problems, security, reliability, compliance related problems that these developers face, we are bringing in a solution where we are not only able to detect them with very, very high precision, but also we are able to provide an actual fix that developers can readily apply on their code after their verification process, of course. This talk will be like basically going over my background, some of the ideas interesting ideas that make the existing detection tools challenging and not as helpful, and then we'll look into like where we are in solving this, but at the same time where the industry is going in solving these particular problems. So it's more on a reflection of how these bug detection tools, in some of the cases, what are the inherent problems there, and identify that. My background, I've been working on automatic bug detection and bug fixing for the last 15, 20 years now. My PhD thesis was considered one of the pioneering works in automatic bug fixing. And I'll do some little bit more introduction as the talk goes on. So I'll just, let me just jump into the talk then. Okay, so I'll turn the video off at this particular time. So I guess you're all able to see my screen. So again, yep, the whole motivation of this talk is my lifelong passion and everything is I have been a connoisseur of good code. Now, what is good code? So a good code, I compare that with a well-maintained garden, where like it's a beauty to behold and appreciate. And that, I mean, when you look into the qualities, what that means is the intent of the code is kind of obvious. It is well documented. When you don't have to like scratch your head and see like what is going on in this particular place. There are good architectural documents, and the code also follows that architecture. There are good test cases where things are covered. You know, I mean, everything that you read about good code in the book, those are kind of the attributes. But in reality, I mean, codes are not necessarily like that all the time. There are like battle scars everywhere. And you will see that those battle scars, if you read the code, at some point the specification kind of moves away from the actual implementation, and the whole fight, as us software developers do, is basically try to keep the code as much drama-free as possible. Most of the times we succeed, and that's why we are able to ship code. But there are many battle stories that we go through. And the intent of this particular talk is to look into one of the tools that help us fix these kind of problems or detect these kind of problems in software early, to help us keep the code as much drama-free as possible, and whether or how much they're working and such. So to take on that garden analogy, there are basically three key activities in gardening that I also find a lot of that they are very analogous to the good coding practices that we have. It starts with a good plan. You need good supplies, good seeds, fertilizer, etc. But most importantly, you need the constant nurturing and maintenance. So I'll just cover the plan and supplies in just 2-3 slides, but the heart of the talk would be focused on that third aspect, which is the constant nurturing and maintenance. So I posit that most of the software, or all the software projects, they start with good intent. They start with a good architecture. I hope so. But what happens is there's a popular saying in the military that the battle plan is only as good as until the first contact with the enemy. So when the actual software development happens, etc., there's a lot of time, or majority of the time, the main problem that we face is that whatever we intended to do, the actual implementation of the actual essential complexity of the code, it is basically taking us to a different direction. Then we have to keep up the architectural documents also consistent, but often we fail to do that. And that's where kind of all the problems start. And there are also places where, because of lack of knowledge and such, or just bravado, we introduce weird stuff in the code. So this is basically a Minecraft. I mean, I was comparing or showing the Minecraft diagram in order to, because that's part of, I mean, it is teaching people to think of good architecture as they're building, but apparently it also fails. So as here is an attempt. This is a Japanese architectural style. It's called Ihu Kenchiku. It means illegal Minecraft architecture. So here you see different kinds of architectural styles juxtaposing themselves by themselves. Like there's this Japanese pagoda style, which is side by side with the German turret style architecture, and also like the boxy styles of skyscrapers. I mean, and obviously we don't want our code to be coming up with these different philosophies and then mess things up. So that's kind of that we need good architecture, but oftentimes that keeping that good architecture consists like throughout the code is a challenge. And there's been many books written about that, and we are all aware of that. And I don't want to go into that. I just want to like allude to that fact that that's one of the aspects of good code where the problem starts. Then the issue is or basically the second point of our gardening activity that I was alluding to was good supplies. And we can kind of pat ourselves on the back that we have already made a good decision by switching to Java, which is we expect one ring to rule them all. But essentially Java has a lot of good things going in favor. Well, I mean, it prevents, like it is one of the modern languages that has stayed in prime for such a long time. And part of that are many of the good design decisions that were part of the things which prevent people from doing weird stuff. So preventing developers from like being very cavalier about the code writing process. That's one of the major things that can prevent people from veering into bad directions. So as an example of what other languages allow you to do, I present here a code written in some language, and it's one of the like top 20 programming languages out there. I would like to open this thing just to get your idea or guess on what this code is.
Yeah, just type it into the chat if you know what language this is, if you can figure that out. If anyone can. No guesses yet.
Yeah, I guess people are.
Oh, Bash. Well, Bash, that's a good guess. That's one guess. And Perl. Tom says Perl.
So Perl is a good guess. Yeah, this is Perl actually. So, and I don't have anything bad against Perl. It's just like Perl has this philosophy that encourages people to do things like that. And what this does is, this is actually not only Perl, it is Perl TK. So it's a very small program, but it's actually a GUI program. It implements a simplified version of the Frogger game. So it's not only Perl, it's Perl TK and GUI, which is like amazing things that you can do with Perl. But it just allows you to do this kind of code that is very, very hard to maintain. And this was the winner of the obfuscated Perl coding contest in 2000, a long time ago. But this is kind of what is part of that of the philosophy. Like one of the, so I had the good opportunity to actually speak with Larry Wall at when I was in the academia. He gave a talk at the University of Illinois when I was a PhD student, and he was mentioning that like his sense of beauty is about like writing concise code, but the more concise the code becomes, then it may also become harder to understand, harder to maintain when programmers not necessarily as skilled as like Larry Wall or somebody who's like very proficient in Perl, they kind of work in a project. So it's not necessarily a good programming language to work and build large projects. And I think that's kind of obvious. So here's a more common programming language, C, very well known, very, I mean, it's one of the classic, like the three, Java, C, and C++. Those three are the key programming language that's out there. Here's a program that has different kind of things in it. So just curious, I mean, can you tell us or make a guess of how many different things are in this program? Thing is pun intended, as you probably understand.
You have to stare at it for a while to get them. It's a little bit like Where's Waldo? No guesses yet? One? There's more than one. Eight. There we go. Well, that's
eight,
closer.
I mean, 8 is the count, but there are, I'm talking about different kinds of things.
Different kinds of things, yes.
So there are actually 4 different kind of things, or thing is used in 4 different purposes in this particular program, very small program. So there is this struct tag thing, which is the purple thing in this particular case. There is also the struct member thing, the blue thing. There's also the local variable thing, which is the red thing. And then there is the 4th kind, which is the go-to label thing, which is the yellow thing in this particular case. And C, it allows you to juxtapose concepts like this side by side. And if you do that, then suddenly your program doesn't make sense at all. So that's part of the pitch for, and again, I don't need to pitch to the choir, because all of us have chosen kind of Java as our passion or our occupation. But these are some of the things that Java does better, that doesn't allow you to juxtapose. Java doesn't allow you to completely keep stuff separate. There are some of the, like, you can mix and match stuff, but in many cases that it's doing things right. And now that brings us to the third aspect, that is the constant nurturing that I was mentioning, and that's where the tools come in. And one of the big things that also Java has done is it was one of the mainstream programming languages that embraced refactoring and program transformation tools very, very early compared to other programming languages. Even if you go to like a C language IDE, now you'll probably see only 4 or 5 program transformations or refactorings available there. And even those could be broken very easily. Whereas Java allows you to do this kind of stuff for a long time. You'll have like over 40, 50 different kind of program transformations that are available in the IDEs right now. So that's one of the good things that we have done. And that helps us. The refactoring tools, they help us in this constant nurturing and maintenance aspect of gardening that I was mentioning. And that's going to be, these kind of tools are going to be my focus on the rest of the talk. So all of this thing, the maintenance, that's the main activity, the software development activity. Hardly we create, if you compare all the activities that we do, creating a program from scratch, etc., is only a small part of the work that we typically do in our day-to-day lives. Most of the work is about preventing software aging. And aging is caused by many different things or lack thereof. So Parnas, in his classic paper in 1994 identified two key causes of aging. One of them is lack of movement, as in your requirements change, but your code is not updating to that. So that's kind of the rigidity, the inertia that is coming in the code. The other thing is the opposite of that spectrum, which is the ignorance surgery, which means that you make changes. So as requirements change, you make changes to the code, but those changes are often done hastily because we're always under time pressure and such, and doing that manually or doing these changes manually doesn't help a lot. So and we don't necessarily use the tools. The tools are not necessarily perfect. All of that, those lead to the ignorance surgery problem, which is the more dominant of the two causes that actually leads to software aging. So we feel like this is our life story. We are constantly in this race. We feel like we are losing, where we are introducing bugs in the code and spending our regular daytime trying to manage the bugs, fix the bugs, only to be successful to a certain extent. And the industry data in this particular case is pretty alarming. Software developers, we are human beings. We make mistakes as we write code. Even the best of us do that. It is well known that every 1,000 lines of code that we write, we typically introduce about 70 bugs, and then we use different kind of tools in order to detect and fix those bugs. We use tests in order to unearth those bugs and fix them. Different kind of approaches. A majority of that, or what I'll focus is on the detection tools that we use. But even after all of these efforts, every 1,000 lines of released code, and I repeat, released code, it harbors about 15 latent bugs. And it is these bugs, when they are found out, at that particular point, you have all sorts of like bad press, like some sort of data breach, or the problems that you know of. So again, I want to have your opinion in this particular case, or basically do a quick poll on like how many of you are using actively some sort of bug detection tools that are available out there in order to detect the bugs that you latently introduce or unwittingly introducing in the code. And what's your opinion, in general opinion on that? If you could.
Muna, are you talking about static tools? Are you talking about like Java test dynamic tools? You're talking about static analysis tools, right?
Yeah. So we are a static analysis company. So basically the majority of the talk will be based on static analysis tools. But I mean, in general, let's talk about bug detection tools, both static analysis tools and dynamic analysis tools. Your opinion on that, and whether you're happy, not very happy, and
yeah. So I'm seeing tools like Lint and ESLint, SonarQube, SonarSource, SonarQube, a lot of SonarCubes.
I see.
SonarQube is pretty popular.
Yes, and
spot bug, and what's the satisfaction like? You're asking, right?
Yes.
So how many are happy, satisfied, could do better? Very good. That's Pierre-Yves Monet says very good. What tool are you using, Pierre? Eclipse. He's using Eclipse. Okay.
Mm-hmm. So the idea of some of the people have
just too many false flags. There we go. That's yes. Sabia says too many false flags.
That's one of that's actually the key feedback that if you go around the industry and ask people about their experience, that's what they tell most of the time. The existing bug detection tools, they generate way too many false positives, and a majority of the time for the people who are consumers of this, they are suddenly overwhelmed with those tools, and sometimes these tools actually operate with 70 to 90% false positive. which means that every 2 bugs that it identifies, one of them is a false positive. And typically these are not very shy. They generate a lot of reports. So suppose you are a programmer and suddenly you are given this thing, 1,000 bug reports, and you inherently know that because of the reputation of the tools, 500 of them are actually not right. So your first goal would be actually going through the triaging process, days and days of triaging, to find out which ones are worth fixing in the first place. And then, and as you're doing that, your manager is saying, why are we not progressing against progressing, or why aren't we fixing stuff, and so on. That's part of our life. And even eventually, when you get to that, your tool, I mean, the tool has only detected. It has not identified, or it has not given you any particular fix. So that's what the so this is basically a quadrant that that I've created based on a report, a recent report done by Forrester on the static application security testing tools. And they basically laid out the tools based on their precision and also the time that are basically the remediation advices that they provide. And the remediation advice, the worse they are, the more time it would require for them to, or require for the people who are the users of the tool to actually be able to find a solution for that. So that also lengthens the bug repair time. So most of the tools, as you see, are in the bottom, or all of the existing detection tools are in the lower left quadrant because of the low precision that all of them have across the board, and also because of their the quality of the remediation devices. In fact, remediation advices. And in fact, there are industry white papers that's written by all of the leading companies like Synopsys, Veracode, Micro Focus, that their #1 priority moving on is to improve the remediation advice that's available. And because that's one of the places where the tools are also not doing very well at all. So here is a very interesting ad that I've stole from YouTube. I hope I don't run into copyright issues.
David,
but
you have one of the worst cavities I have ever seen. Okay, have a good day. Aren't you gonna fix it? Well, I'm not a dentist. I'm a dental monitor. I just tell you when you have a bad cavity.
Why monitor a problem if you don't fix it?
So that's the problem, or that's the position that actually when I started my PhD thesis about like 15 years ago, at that particular point, I started asking that question. What if there were services that not only detected vulnerabilities, but also fixed them automatically? And so this work, as I mentioned, my PhD work at University of Illinois, it was identified as one of the key works that that introduced this concept of automated software fixing. This is my research group in University of Illinois. Just to go back to the stories, my advisor Ralph Johnson, he actually did the original work on bug refactoring, or original thesis on bug refactoring, on refactoring tools. So we at Illinois, we considered ourselves as the refactoring capital of the world. But I was coming up with expanding the refactoring envelope in my PhD thesis into a domain where we are not only able to detect security, reliability, and compliance problems, but we're also able to fix them with refactoring, so that we make changes in the code that are not only behavior preserving. That's what the refactoring stops. So pushing the refactoring envelope, that's kind of where we wanted to be, or what we wanted to do. So then I moved into the academia. I was an assistant professor at Auburn University. This was a part of my team at that particular point. We actually built the first bug fixing tool, automatic bug fixing tool, back at Auburn University in 2013. And that particular research work at Auburn University, it received the best computer science research in all disciplines of computer science in that particular year. And it was awarded by ACM. And it was awarded at the ACM Turing Awards ceremony. So that was one of the big boosts. That's when the work started. But then I moved on. I was a part of, I joined Coverity. I worked there. My team at Coverity, we released the first bug detection tool for JavaScript and Android applications. So I forgot about this. So this was the one of the photos from that award ceremony that I was mentioning. So this is us, myself and my student, who is right now finishing his PhD at Carnegie Mellon, and he is we are with Vint Cerf, the father of the internet, at that Turing Award ceremony. Anyway, so then I moved into Coverity, and in 2017 I started Open Refactory after I received an award from the National Science Foundation to basically start, take this idea from academic research into what we have, into basically a product. And right now, as I mentioned at the top, that we have two different products, one targeting the problems of Java developers, and another one targeting the problem of C developers. Now I'm going to get to that near the end of the talk. But let's come back to that original question. What if there were services that not only detected vulnerabilities, but also fixed them automatically? That's the question that I was introducing. But the existing tools, the bug detection tools, they are only focusing on the first aspect, which is good. They are very, very valuable. But this problem of a lot of false positive, this is predominant, and everyone who's used these tools are aware of that and unhappy about it. So what I will identify in the next part of the talk is identify 4 different challenges that are there already in these static analysis tools, or these static analysis tools face. And because of that, they lead into all sorts of false positives. So at the end of this talk, you basically will get an intuitive understanding of why your SaaS tools will be or are getting all sorts of these kind of false positives. And basically, you'd be able to appreciate the underlying problems that prevent them from getting better coverages. So basically all of the main problem when you talk about the lack of precision, it comes because we are not able, or you are not able to keep track of all the paths in the program. A program has many different paths, even the simplest ones. You basically look into a program, and there's the paths are exponential, and it's only a number of paths that you can keep track of. So majority of the static analysis tools, they take the easy route, and they stop keeping track of creating an keeping track of all the possible paths. And after a point, honestly, it gets impossible to keep track. It is impossible to keep track of all the parts of the program. That's just computationally intractable at this particular point. But people bail out early, or the detection tools, because they started about 20 years ago, many of them with very limited computing power. So all the engines that they were built upon, the mathematical model that they create, they become a statistical model. After a while, they're just guessing about which paths are being taken and which paths are not. And that is creating a lot of these false positive problems. That's the one of the fundamental things that create this kind of stuff. So here's a very simple Java code, not necessarily the best written code. So I just, like, in order to keep the illustration simple, I kept the variable names. I apologize, variable names to be something that we should never do. But just I mean, this is good for illustration, because we can refer to that as variable ij, etc. So the question here is, or the question here is whether this call to j.bar, whether this is safe or not. And in this particular case, it is safe. We can look into this code. It's pretty straightforward, and it is safe because there is this place where, like just a little bit higher above, where we initialize that particular variable. And the key thing is that the guarding condition under which that initialization happens and the guarding condition on which that use happens, that's the same. So even if you're building, think of that from a tool builder's perspective. If you're building a tool, you can just like even do just a naive tool builder. Let's say even if you're doing just string matching of these constraints, and whether that constraint is the same as this constraint, then all of this is good. We can identify that this is a safe invocation of the bar method, which is all good. And that's all what everyone does. Now let's modify the program a little bit. We have, instead of I not equal to null in the lower part, we have I equals null in this particular case. And again, the question is whether j.bar, which was initialized up above there, whether this is good or not. And clearly, this is not good. This is unsafe. And the reasoning here, again, from our perspective, and also from the tool's perspective, you can codify that pretty easily, that the condition under which the initialization happens, that is completely opposite or complementary to the condition under which the method is invoked. Again, that is pretty straightforward for us to understand. It is also not very difficult to produce, to explain that to a tool. We can have basically a kind of a SAT solver to be able to codify those paths and be able to identify that, well, the condition under which to identify that this j.bar is inherently unsafe. So again, that's what all of the tool builders do. So the problem is still not there. But here the question becomes a little bit more complicated. So again, we have this j.bar. We have this. And in this case, we can identify. If you look at the code closely, we can identify that this is safe because again, the initialization happens up there. But the condition under which the initialization happens, it's actually, it subsumes or covers the condition under which the use happens. So you will be initializing the code in the cases where you're able to use that. And this is much harder for people or basically to tell a tool or teach a tool to do. So that's where one of the first problems come in. Like how do you tell a tool to keep track of conditions like that, and because and then the computation becomes challenging. And imagine that you are doing it with millions and millions of paths in the code. Then at a point it just becomes computationally hard to do that. And then there's the halting problem in the code. So here is, again, the same problem. We question whether this is safe or not. In this particular case, we cannot tell, as we were being able to tell or have a guess beforehand. Right now, we're not able to tell that. So here, there's a particular constraint under which this is initialized. But then whether that constraint is whether k is less than some method, whether I is less than equal to some method, etc., we don't necessarily know. So this is so there is no relationship, or the relationship is very, very hard to create between the green constraints that under which the initialization happens with the blue constraint. And this is something that is computationally very, very hard. And frankly, that's where the imprecision is going to come in for all the tools. Even the best ones, there is, it can at best do some approximation. There's no way you can identify that. And because of that, so the point is that we can never get rid of false positives. There would always be some false positive. But the current reality of the 70 to 90% false positive, what can we do in order to minimize that? That seems to be the fundamental question that we need to be asking. And all the tool developers, the detection tools, the fixing tools, etc., all of them needs to be asking. And many of the existing detection tools, what they do is they have taken the easy route. Again, because most of these cases, the technology was built like 10 years ago and such. So changing these kind of fundamental analysis technologies is very, very hard. Trust me, I've been there in the detection industry and I've seen those kind of things, how hard it is to roll out an existing algorithm that works and into an algorithm, even though that is better, it takes years, 3 or 4 years actually, in order to do that kind of swapping. That's kind of what happens in the bug detection industry. So I'm showing this photo of Holmes and Watson because often in the Sherlock Holmes stories, you get into these comical scenarios where Holmes is asking Watson, like, can you look at this person and tell me about that person? And what Watson does is comically make some shallow guesses. And as a result, whatever his guesses are completely false and utterly false. And then Holmes basically does that again. I mean, you've read that, you've seen that elementary, my dear Watson. I mean, that's kind of, I mean, everyone knows about that. So Holmes comes in, he does a thorough analysis of that particular person, and then he's able to provide better guesses or better estimates about the traits of that particular person or that subject. So that's the difference where the existing tools, unfortunately, many of them are still taking the Watson route. There's a lot of statistical stuff that's going on there, where the computation is right now available, where you can actually do some of these Holmes-like things. And that's just what the existing industry is not doing at this particular point, and that contributes to your false positive. So, and to be fair, scaling, the main problem in this particular case becomes scaling. So you can do deep analysis, but can you scale that with millions of lines of code? That's the trade-off that the existing tool makers are doing, and that's where they're making sometimes decisions that are not necessarily helping the rest of us who are the consumers of the tool. So that's kind of the first aspect of insufficiently creating a model of all the paths that's taken in the program. So next, the other problem, the second problem that I was alluding to, it comes from hidden paths in the program that are not necessarily obvious from the program path. So as Java developers, we are very, very much familiar with using frameworks. That's kind of our second nature. We use this kind of frameworks all the time. A lot of the knowledges, I mean, frameworks are all about inversion of control, etc. You all know that. We don't need to go into that. But what this inversion of control basically does is there are these flows, control flows, data flows in the program that are consumed inside the framework or coded inside the framework that is not necessarily obvious in the Java code. So if your analysis tool is only analyzing the Java code at that particular point, you are not able to make very good guesses. So just to get a start on that, the very simple framework, or it's not necessarily a framework, but something that is underlying, that is not necessarily obvious, is how we use threads. I mean, that's very, very well known. So here is, again, we are asking this question of the static variable global.s, whether this invocation of length, is it safe or not? In order to do that, we basically, like, just isolatedly, if we look into the run method, we don't know who's calling run. So at this particular point, we don't have any idea. But in reality, this global.s is being initialized there in the method foo, and then you initiate a thread, and what it does is the start method in the thread is actually calling the run method, which is the hidden thing done by Java. And that's what tells us that, well, this s.length is not necessarily, so there is no problem in this particular piece of code. And if you don't have that information and you are making bad guesses, you will be generating false positive. And if for some reason global.s is actually not initialized and you are not able to follow this kind of path, then you will have false negatives, as in you will not be able to identify, or your tool will not be able to identify that there is a problem in the code. So that's kind of a very simple framework. The underlying or hidden knowledge about control flow or call basically call hierarchy in the program that we need to account for. So in reality, the frameworks are much more complex. So here is a very simple Android program that I copied from one of the popular research papers.
Hey, Munawar, Charlie here. I just got an interesting question. Do you want to go back to the previous slide? Yes. I got a question here because someone was asking about what happens if another thread makes a global.s call, basically.
Yes, that's a very good question. So essentially, you need to be able to identify all different paths. So this call from foo, initializing s, and then calling run, that's one path. There may be other parts of the program, like bar, etc. Foo may actually have a for loop, etc. So there could be many paths which may allow us to come into run. And that's where the path problem comes in, the previous one. So you need to account for that. So you may as well identify that some paths are safe and some paths are not. And you need to tell the developer that these paths are safe and these paths are not. So that's the remediation advice, or that's where the even the like if you're generating warnings, the way you identify the bug that needs to cover that particular thing, because without that you don't know where to do the fix. If you're fixing in the run method, you are doing sometimes an unnecessary surgery, and sometimes it may be wrong.
Yes.
So you need to be fixing at the place, let's say a bar method, where the initialization did not happen. So you need to be able to identify these different paths and do that. That's a great question, and that's also is part of the fundamental problem why these tools are pretty complex and such. So I hope I was able to answer that.
I think so. Yeah.
Yeah. So let's go back to that Android program. So here's a very simple activity in Android, which has this method on restart, which is one part of the Android event flow. And this on restart method gets a password from some part of the GUI. So essentially, we can identify that this is tainted, or potentially this is tainted. So from there, the taint flows to this variable pwd, and then it ends up in this this.user, this particular object that we have instantiated that harbors that potentially tainted or at least sensitive information that is coming from the code. And then there is this part of the code. So the same class activity, but there's some other method that I'm showing here. This is basically a callback method for a button click. And in this particular case, the question is, where is this method getting invoked from? So here we are using this user dot, or basically the password that we have stored before, but we are not sure in what path this send message is executed. And again, that's we understand that this send message, it happens somewhere when the activity is running. So it happens somewhere in that green region, and that's when that gets invoked. But then the on restart method, where the taint was initially introduced, that is part of this loop in the Android lifecycle, and that's where the taint may get introduced. So if we happen to be in a place or in a position where that on restart gets invoked and then eventually you lead to the send message, that's when you are able to get a particular error. And in another control flow, like if you're going from on create, on restart, etc., to send message, at that particular point, there are probably not any errors in that particular case. So that's kind of the idea, again, hidden in the framework, oftentimes hidden in XML files, etc., that we need to account for. So in this particular case, once that connection is being made, that there is data flow from on restart, and the taint that is created by on restart is flowing into send message. So we can identify at that particular point that PWD is getting basically a good, basically getting tainted, and that flows into PWD string. It goes into temp, and eventually it gets into a text message that's being sent out. At that particular point, you have an information leakage. Your hidden password or secret is being leaked out to who knows what. And so that's the fundamental problem that is brought about by the frameworks. The existing detection tools, unfortunately, do not account for these frameworks. So they're not able to codify. I mean, they can, so what the existing tools do is they make a best guess for some of these framework cases. So they maybe the popular ones, let's say Spring or maybe Android, they have some hard-coded identities where they're able to describe that and be able to encounter that to some extent. But there are hundreds of frameworks out there, and we use different kinds of these frameworks for many different reasons. And if our detection tool is isolatedly looking into code without knowledge of these frameworks, then we are getting into false positive or false negative. So that's the second problem that we are alluding to. The third problem is that we are living in a polyglot world. 96% of programs in GitHub are written in at least 2 different programming languages. Many of the programs are written in multiple programming languages. So here is basically an example from our Open Refactory code base, basically a cartel down version of that. But here we're making a GenI call, which is very, very common from Java code, where this prepare Dimax method is called. And then we are calling this method that we have implemented in C++ in order to make it faster. And that's something that many of us do. So the question is that kind of information or basically our tools need to be able to go across the boundary. So not a Java tool should not only know about Java, but also know about other programming languages. And typically this kind of interaction in a polyglot world is known as an execution interaction, where there is a host method. In this particular case, Java, some method in Java is going to call prepare Dimax. Here, I'm not showing that. But then there is a server method or a guest method that, sorry, it's the opposite. There is a guest method that is actually calling that, and there is a host method which is actually hosting or solving that particular problem. And then we need to be able to connect these two and analyze these two together in order to get a better picture of that. And so coming back to that Android example that I've shown you, even when we're doing this thing, r.id.username, we are essentially getting that information from some XML file, let's say an Android layout that was there. And that information needs to be codified, that information is coming from an XML. So here, this kind of interaction style is known as a data loading, where a data is kept in a low-level language like a JSON or let's say a YAML or XML for that matter, and you are consuming that thing, and your analysis needs to be aware of those kind of things. So the same for password text in this particular case. There is also the case of shared ID, where something is identified in, or this is another kind of interaction mechanism. Something is identified in the code or in XML. So for example, in some sort of layout file, we have identified that for the event of a button click, let's say the send message method needs to be invoked, or this callback method needs to be invoked, and that's what the framework integrates. So again, here, in order to do that correctly, you need to be able to aware of not only Java, but also JSON or XML in this particular case. So this is again another problem that has been there for the existing tools, and none of the for the existing applications that we write, and unfortunately none of the tools are able to do that. Here's another example of a shared ID, which is even more complicated. So again, this is a very small XML specification for a Spring framework, which is also using aspects. And what this is saying is that this data access operation, when you invoke that operation, the do access check method will be invoked before that. So control flow information like that, control flow and data flow information like that are encoded in XML, and those need to be expressed in a way so that we are able to handle those particular things. So that's the third problem that I was alluding to, and unfortunately the tools have not been able to cope up with that, and that's where we come into all of these false-positive problems. And then there's the emerging problems. There are, we started with like all of the bug detection tools, they started with security, reliability, compliance as their goal. But there are emerging domains where if we have a fixing capability available, they can be also useful in other domains. So one of these domains that I have worked on before is actually using code rewriting to improve energy consumption in code. So can we modify our program so that it consumes, or it has a lesser energy footprint? It consumes less energy. What that would mean is that your cell phone or your software application that you're writing on a cell phone would not be draining your battery as much as it is doing now. I mean, that sounds like a very cool idea, and we have done some background work on that particular thing. But this is just again an idea of the emerging problems where we can use this kind of fixing technology available to actually do more cool stuff than what we are already doing. So just to give you an idea of what we did there, in Java programs, we looked into the collection classes. So this is the collection class hierarchy, well known. We looked into the collection classes, and we tried to identify for the common tasks that we do with collection classes, what kind of or how much energy is required or consumed by those kind of issues or those kind of operations. So here is the hardware infrastructure which we used in order to test this thing. This was done back when I was in Auburn. So I was in Alabama, or we were testing this thing in Alabama, but this actual hardware was in Calgary, in California, with one of our research partners. I mean, thank God for technology. So we were able to basically execute well-known operations that we typically do with collections, and we created an energy profile of how much energy is being consumed by each of these cases. So if, for example, we are doing comparing various kinds of lists that are in Java Collection Framework or JCF, we also compared with Trove library and also Apache Common Collections library. If we do those, and we are essentially doing just insertion at the beginning of the list, intuitively and also in reality, linked list takes the least amount of energy. It has the least energy footprint. And unless you have a clear motivation for doing that, you should never use tree list. That kind of is the lesson that you can take out from this particular energy profile. If you're inserting at the end of the linked list, which is a more common operation or a more typical operation in the case, then essentially the top, tree list is still bad. Again, unless there is a practical reason or a essential reason for you to use that, you should never do that. But then all the other kind of lists, they're kind of very close. So they're not that bad altogether. Essentially, in this particular case, the tint array list, which is implemented by Trove, is better. But as I mentioned, it's just like apples and oranges, not very bad. So by creating these kind of profiles for different kinds of popular operations, you are able to basically create a heat map of things that you can look. So where you can compare stuff, where the green means good and red obviously means not good, you can basically get an idea of across the board for different kind of operations, the typical operations that we do with a particular kind of list or set or map for that matter, which ones do better. So then with this kind of knowledge at your arsenal, you can ask the question, or we ask the question, now can we programmatically make changes in the code so that we can make sometimes good changes. A good change means that we were using something that would consume more energy and we swap that with something that would consume less energy, or we do something, sometimes, I mean, just for experimental stuff, we can make bad changes, as in something which was consuming less energy, we swap it with something that would consume more energy. And we want to see if we do that programmatically, what kind of impact we had. So in case of Google JSON library, well known, we made 51 bad changes. And we were able to worsen the energy consumption by about 3 times. So that's kind of the consequences that we have. Sometimes unintuitively, we just use one kind of collection as opposed to another, and we are not aware of the consequences because nobody has told us so. Well, a tool can tell us and actually help us modify the code in order to get to a code that would consume less energy. And sometimes the effects are not, subtle, but often, but every other time, like it's the cases where we had 3x more energy, and you are able to reduce that by 3x. That's when the significance comes in, and more often than not, you would be able to see if you are using or if you have access to these kind of tools in practice. So here, there's also a very small application, a stock exchange trading simulator that we got from GitHub. We made like 8 good changes in that I was mentioning. In that case, we were able to improve 38%. And as I mentioned, some of those cases, the improvement are not that dramatic, but some of those cases are. But overall, like if in your case it comes out as valuable, then there's a value that is very, very hard to pass. So that's kind of like where the existing tools, they can come in and potentially try to address some sort of future kinds of problems. So that's kind of where, so we have identified 4 different kinds of issues and talked about what the shortcomings of the existing tools are. Now let's talk about, I'm coming near the end of my talk, so let's just talk about how Open Refactory does some of these things. So at Open Refactory, our mantra, as I mentioned, is that we fix code automatically. We help software developers achieve higher security, reliability, and compliance goals. So the intelligent code repair, which is our product, it right now focuses on Java and C, as I mentioned before. This combines 3 key aspects of research done on deep static analysis, where the first part, remember the thoroughness, basically the question that we asked was, can we do deep analysis of the code and be precise and also be able to scale that for large, as in millions of lines of code. So that's what the deep analysis comes in. There's also work on machine learning that fuels this thing, which basically in this particular case, when we generate fixes in some of the cases, then and by the way, we don't generate fixes in all of the cases. Right now, for all the bugs that we identify, we generate fixes for about 60% of the cases. And as we go ahead, we expect that we would be continually improving upon that. So, but in reality, we don't expect that we would go beyond 70 to 80% of the cases where we can actually provide an automated fixing. But if we do good fixes, as in fixes that look like what developers have otherwise produced anyway, which is where we use machine learning a lot in order to curate fixes like that. And also, if we are able to create a tool that detects with very low false positive, then that has an inherent value altogether anyway. And then we also do the code refactoring technology, which allows us to do modification with surgical precision. Essentially, you would only want to modify and remove the bad part of the code, the tumor in the code for that matter, and leave the rest of the organs intact, or the good part of the behavior of the code intact. So that's where a lot of work on refactoring, on my background, etc., comes in, and that's so the solutions that we provide do not introduce more bugs or new bugs in the first place. So right now we have for Java code about 60 fixers At this point in the release that we're coming next, we'll have about 70. So we are coming up with new fixers all the time. And think of these fixers as like a band of Marvel superheroes, where each of them has a specific capability, and together they're able to like save the world for that matter. So the key benefit that our tool brings in would be that it would reduce the mean time to repair bugs, which is right now 120 days. It would improve the developer productivity because it would not waste your time by generating a lot of false positives. And then in the majority of the cases where we actually generate, where we detect something for you, it is already a bug, and we also have a solution there for you. So that would reduce the mean time to repair bugs and also improve the developer productivity. That's how we are stating. As far as benchmark data is concerned, on benchmark, Open Refactory demonstrated less than 3% false positive. This was done on the Summit benchmark, which is created by NIST and Department of Homeland Security and Department of Defense. This is kind of the go-to benchmark that the rest of the detection industry follows. Basically, they want to find their efficiency in the code. Oftentimes, their efficiency is better than 50%, which is basically, so essentially like every 2 or 3 bugs that it identifies, one of them is a false positive. In our case, every 20 bugs that we identified, we were only giving 1 false positive. And in 86% of the cases on the benchmark, we were also being able to generate a fix, a complete fix that you can apply readily in the code. So that's where we want to be. We want to be a tool which would have high precision, because we are thorough, we are not necessarily as fast as the other tools. Like, let's say 100,000 lines of code, a typical Sonar source would probably run like, let's say, a minute on that in order to scan. Like SonarQube would take, let's say, about a minute. In our case, will probably take 10 minutes, but then we'll be generating 10 times fewer bugs than, and the bugs that we have we will identify, they will have, they are actually critical bugs that developers care about. And we have like several different bake-offs that we have done with all the existing, with like majority of the, or many of the existing bug detection tools that are out there. And that's something that we have seen across the board. So ICR is available in 2 ways. This is available as a pay-as-you-go mechanism on the cloud. So you can just go to Amazon right now, just search for AWS and AWS Open Refactory. You would be able to go there. There is a 7-day free trial that is available for you, where you can try this thing out. And what that and after 7 days, you just be paid. You'll just be charged hourly. So essentially, you are just using it as a pay-as-you-go mechanism whenever you want it in your QA cycle. So right now, we are available in EC2. By the end of this month, we expect to be available in Microsoft Azure Cloud as well. This is, by the by, not a SaaS. So Open Refactory doesn't see anything of your code. This is entire the machine. So what essentially this solution is an infrastructure as a service. So you control the code base, or you control the machine. It is just pre-furnished with Open Refactory software, and so therefore you have complete control of your code. And Open Refactory, or other than Amazon or the cloud hosting service, which you are probably using anyway, nobody is able to see your code, which is the most precious thing. If you are not willing to do that or make that compromise, then ICR is also available for an on-prem deployment. That is, in this case, you can also choose for an on-prem deployment if you actually see that you're using the cloud tool often enough, so that there is value of using that, or make that a part of your CI/CD pipeline. And so we have that kind of solution also available at that particular point. And again, you can contact us. We can give you a 7-day, 15-day trial license in order to try that out in your own premises. So that's kind of what we have right now. We have a Java and C solution. The key benefit that we bring in is we are Holmes-like thorough, and therefore we generate dramatically reduced number of false positive compared to all the competition that's out there. That's the key benefit. We are also working on, so we are the only company that right now, as far as I understand, are working on this generic framework aware solutions, where essentially we'll have our meta language that we will generate. You don't have to do anything, that we will use to specify different kinds of frameworks, and then our engine will be able to understand that particular framework and be able to handle those things. So we are in this particular slide, you also see that that we are like on our way to supporting some of the well-known frameworks, and more are going to come as we go ahead. And finally, so near the end of the year, we expect to have an ICR for Python. And the other fundamental thing when we are supporting the framework is also the related is the third question, the idea of the data loading and shared ID kind of interaction, where you also need to understand the meta information of the code that is encoded in XML or YAML or JSON, and be able to integrate that in your overall understanding of the framework, and that improves your thing. So that's where we want to be. And the energy thing, that's something that we are working on right now. It is going to come at some point in future. It's not integrated in our tool yet. So I would encourage you like we are very excited to bring this tool to all of you guys. Get your expert opinion, feedback on what works, what doesn't, and help us make this thing better. But essentially, we expect that the future is fixing, and that's where we state ourselves to be in the long run. So with that, I'd like to take questions. Thanks a lot for your time.
Got one question here, and I'm just typing something into the chat about, is it possible to have a one-shot free trial? I'm just going to respond to the chat, but the answer is that, yeah, when we were in the Amazon AWS deployment, when you launch the instance, actually the Navigator box that we showed you on the architecture there, you can just use OAuth to authenticate with GitHub or GitLab or Bitbucket, and if, once you've authenticated that way, because we don't see those credentials, you pass those credentials to OAuth, then you can just point the instance at your GitHub repository, pick, your projects will appear, pick a project, and say go. And that's it. There's no other pre-processing config or anything that you need to do.
So we take pride that it would take you less than 10 minutes for you to actually start your analysis. And essentially, as Charlie's mentioned, you just buy an Amazon machine or a cloud or an Azure machine. You connect it with your browser. You basically point it to your source code repository. Right now, we support GitHub, GitLab, and Bitbucket. And also, you can point to your local disk, and if your project is there, and then you're able to run it. And the on-prem deployment, it also is done the same way, except instead of being hosted on an AWS cloud machine, it will just be hosted as a Docker container, and you'll be able to host that on your on-premise thing. So you can, as seen here, you can go to our website. You can also search like AWS Open Refactory and be able to go to our cloud offering. And for on-prem deployment, just email us at info@openrefactory.com, and we can work.
Yeah, I was just going to say, so the 7-day trial isn't just for one project, right? So you'll get it for 7 days.
You can run anything that
you can run as many projects as you want in that 7-day period, a large project, a small project, yes. And see how it works. Any other questions? I'm wondering, Courtney, if people want to ask questions now that we're kind of done with the presentation, is it possible to unmute, or is that if people want to unmute themselves to ask a question, that might make it easier than typing into the chat?
Perfect. Let me see if I can do that. Okay, I'm going to ask all to unmute. It'll prompt you on your computer if you would like to unmute. And if you have a question, feel free to do that. Just sent it. If anyone has one, feel free to hit that and then ask away.
Great. I'll put my pirate video back on now since we're asking. And you made it through the presentation, Munawar. You can put your video on now too. I think we're past the.
Yeah. Let me show. Yeah. So the internet held up. That's pretty.
That's good. Seeing if there's any other.
Peter is saying something. Peter, you're muted.
No, Peter's not muted. Or is he? Oh, no, you are muted. Peter, your lips are moving, but no audio.
Yeah, I don't have the ability to hit unmute on you either. Oh.
Yeah, well, he's unmuted. I think it's his microphone may not be enabled correctly or something.
Yeah.
And thank you, Alan. Here we go.
Oh,
yeah, you can kill your screen share too. That would probably help 1 hour.
Okay.
cool. I just wanted to say thanks,
There we go.
Monwar, for joining us and presenting. Unfortunately, I missed a little bit of it, but I really like what I saw. Thank you. And yeah, folks, if you have questions, this is a good time.
So Kenny asks Munawar, and this is a great question because we know a lot about find bugs. He said, for the static analysis part, how is this product better than find bugs?
So I can, so find bugs is, I mean, I know Bill Pugh very well. I mean, we go back in the research. I mean, when find bugs came up, I mean, and he knows about my research work, etc. He's doing. So find bugs is at this point, actually find bug never wanted to be a tool that had very high precision. I mean, that's probably a very controversial statement. But what find bugs really wanted, or this was the first demonstration where basically there was a whole lot of problems that you can identify. So find bugs finds a lot of stuff for you, many of them shallow. But at the same time, in order to do the precision, you need to do a lot of computation. And that's where find bugs never really went. It's majority of the analysis that it does are actually structural kind of stuff. It identifies problems in structural issues. So that's where the issue of find bugs would remain, as in it would find structural things for you, but wherever you would need deep data flow analysis in order to have high precision, that's where find bug or spot bugs, as they're known at this particular point, they will be lacking. Just to give you a comparison, so there was a recent case where we were looking into a small program, like let's say 20,000 lines of code. I think 20,000 lines of code. We were able to identify 11 problems in that particular case, all of them serious problems. There was one false positive in that particular instance. Then we ran some well-known tools. We ran find bugs, we ran sonar source, we ran Codacy, etc. on that same program. We wanted to find out, well, what they're doing. So I don't remember like the exact numbers, but find bugs, I think, had 200 problems identified in that code. Sonar source had 120, Codacy had 150, something like that. And clearly that 15,000 lines of code did not have that many problems. Or even if in some of the cases, some of the things that they identified, they are like code smells, but people don't necessarily care about them. So that's where the fundamental problem is, that in the industry, the tools that are out there, they will just create too many things for you. I mean, anybody who have consumed a sonar source or a find bugs or any one of these reports would see hundreds of these kind of things that are being reported. And now you're wondering which ones are serious, which ones are real, and then what do I do? I have to fix, and that's the hurdle that we want to.
Yeah, and in a 20,000 line program, okay, and 100 bugs, but you get into programs like the size of Jenkins, which is 500,000 lines of code. Then it starts to get pretty onerous when you realize you might be triaging hundreds and hundreds and hundreds of bugs, trying to figure out which are the ones I really need to pay attention to. So as the projects get bigger, it's that much more critical to get the false positives down to a manageable level.
Sure.